Okay, so first, thanks organizer to have me here. I was not involved 2009 the program because that time I have not been discretized. And I get in this field is thanks for Paulus because he drew me attention about continuous symmetry for discrete equation. And I thought, oh, that is something probably I can do because I work on a lot about generalized symmetry for continuous equation. So, and indeed, and we managed for even brought a recursion operator, Hamiltonian structure for the discrete equation, but that is not what I'm going to talk today. Today, I talk something which is a project we work on, and with my PhD student, George, he's here, and Mikhailov. And we will discuss about the log representation with reduction group. Right, the first I draw this graph and for logs double scheme, which you already heard, and this saves me a lot of time to explain it. But if you look where the arrows, you notice that something here is a center, okay? And all arrows come from here. That is the logs operator. So if you have that operator, I will now little bit mysterious to say proper logs operator. Then you can define your double transformation, double matrix with associate with the linear map, which is shift. I will assign as S. And then you from there, you get your double matrix. And then from the commutation, you got this differential difference equation. And then you can construct another direction one. And this Bianchi commutation give you the discrete equation. And that both, this is what I want to stress, they are symmetry of this discrete equation. And when you look at the picture, you also should map this to another side, and they are exactly done for another operator, A, which is the one mentioned in the previous talk, that the sequence of community operator, which will produce the hierarchy for partial differential equation. So since that is the central operator, and now we will write this operator is dependent on two parts. Basically, you have your potential U and spectral parameter lambda. So for given equation, to find this log representation is very hard. There is no algorithm to do so. I think one successful method probably people use is focused Easterbrook prolongation procedure. But this highly based on your answers. If you make correct answers, bingo, you got it. If not, then you will struggle a little bit and try quite a lot to get that. But we can approach that from another angle. Instead of a start equation, we just purely look at the operator. And that is what they do a classification for possible log representation with their reductions. And you have to add reduction in, because if you don't do it, you will have very complete, huge system, which does basically nothing for you. So since we do the commutator with two operators, it's always naturally to think that this U should be sitting some Lie algebra. So for finite dimension Lie algebra, and we know you have direct sum with this radical solvable algebra problem plus this simple part. And the simple part you can also decompose as simple Lie algebra. So the basic start is you will take some simple Lie algebra, and that is Lie algebra part. But you also need to think about what's going on with your spectral parameter, the dependency on the lambda. So for lambda, you use the fraction linear transformation. And for if you're in the finite dimension, and there is a classification for this transformation, a simple group. There are 5, and they have for this Dn, and the one is I'm going to talk. Oh, right. Why I'm going to talk this is a Dihedral reduction group Dn, and also have for this T, it's tetrahedral, and O, and octahedral, and icosahedral. And this 5 simple group is a finite group. And let's go back. What I'm going to get to the message today is come from my corner from continuous or classical integrable equation. And what I want to do is I just bring the method which we used there to here. And now I want to bring in reduction group for the double transformation. And I also draw your attention, and if you use the normal way, you may go to your double transformation. Somebody say backload transformation, and I'm not sure which terminology I should use, but I will just call double transformation. And it's not evolutionary one, and I will try to make it evolutionary, give you some idea. This is not a theory yet, and it's purely based on observation. So the plan is just to concentrate on the Dihedral reduction group and construct rank 1 double transformation and make it find the log operator, go backwards through the double transformation, go backwards, find the log operator for the evolutionary flow, because that will give you the generalized symmetry for your discrete equation. Because that is the point if I want to bring in recursion operator and Hamiltonian structure, I have to get evolutionary flows. So the Dihedral group is generalized by 2 elements. One is rotation S and fraction R, and they satisfy the condition, and that is have order 2n. And this one, if you, because sorry, I got in the wrong place. So if you on your space, which is a complex plan for your spectral parameter, and this group will write into this fraction linear transformation, and the correspond sigma s will be just omega times lambda, and this omega is the primary root of unit, nth root of unit. And one is correspond the reflection. So if we forgive generic point on your complex plane, and as you can say, your orbit will have 2n point. But of course, if you choose a special point like 0, you will have only 2 points. One is 0, one is infinite. Okay, that will later on we will say that is will determine how we look at the poles. So that group and will inherit for our logs operate, and which is on the L operate, you need have transform that, and to this is the same, and the reflection is that T is a transpose operation, and the Q is a diagonal matrix, and on the diagonal and on the I place is the power of your here omega if your is primitive for root of nth root of unity. So for this operate was first appeared in Mikhailov's paper 1979. It's also in this paper the terminology reduction group originated. And the correspond the integrable differential equation is that one, and have constraint on the phi is add together is constant, and this is how you define theta. So if you look at the periodic on the phi, and then you will fix your n, you will have n minus 1 component normal evolutionary systems. But that one, if you do n go to infinity, take the following continuous limit, you get our famous Kp equation. And instead of your fixed periodic on this I, you can also think about this system as 2 plus 1 dimension lattice field equation. And so if in the periodical case, you look at phi 1, phi 2 as independent, as dependent variable, and otherwise you look at that as a shift. Okay, so that is where the shift things come in. And if you look at the theta, that's why this non-local term come in. Okay, so that's some work have been done for this system, and the one I want to mention is the next one is beautiful graph. So when you fix your n, that is 1 for n equal 5, and now you just you got this is Barry got that is Mikhailov's student produced that I think 2008 or 2010, and that is normal evolutionary 4-component system. And if you look at the intersection of the Soliton solution, is Y shape. That is more like a 2 plus 1 situation. So that is the reason I look at this system. I also studied the recursion operator for this for n equals 3 even only, and they have quite a particular situation. And normally you have your recursion operator will split as Hamiltonian and symplectic operator, but that one, the recursion operator itself will not have such a structure. Have to go for R square to do the splitting. So I will not talk too much about this graph because that is not my work. But the way they got that is use dressing method, and the dressing method is closely related double matrix. So that's why I included that one. So the Locke's representation they used for produce the integrable differential equation is that one. And the delta is just like a shift periodic operate. And phi is diagonal matrix. And I put this n here just later on I will have a nice expression, but you could just take 1. And now what I did is instead of I is down index, I put up because that will be my component instead of shift. I just want to make a distinguish this notation. And I talked about the orbit for this Dn. And if you look here, where is the pole sit? The pole is at infinity and 0. So they took this kind of like a degenerate orbit to get that operate. So we want to, for this one, instead we look at the double transformation. I want to have a generic pole at lambda. So instead of I follow here to do lambda 1 over lambda, I put a pole at a generic point mu. And here C is diagonal matrix, and at diagonal I put in Ci at II position. And A here is n times n matrix. So I would, when you have reduction group, and reduction group, your log representation is invariant on this reduction group, and I would like my double transformation also invariant with respect to the same reduction group. So the reduction group on the double transformation, because the double transformation is a group object element. So, and your L operate is sitting in the Lie algebra, but this is in the Lie group. So that is inherent. The group action is the following way. So if now I want to look at my double transformation on the what condition will be invariant on the Dn. If I basically, on the assumption that 1 is automatically satisfied, only thing I need to check is the first one. I put that in, and you compare with the poles, and you get that two condition. So you notice if I take a non-trivial matrix A, which means I take the determinant not equal 0, and this one I can do A inverse, that I will determine relation between A and C, because Q is my diagonal matrix. And then I can use this condition, reduce my double matrix. It's like that. That is trivial. So this means I should not look at non-degenerate A. I should more look at the degenerate one. So then I make answers. I'm start to look at my matrix with start simple case will only have rank 1. So if it's rank 1 matrix, and I can present it as this, basically you think this as A and B, they are n-dimension 2 vectors, and is the matrix you write as n times 1, and then 1 times n, and that I produce my matrix A. So if I make this assumption, and what happened, and of course AI, they are component for my vector A, and BI, a component for my vector B. And what I notice is my B will be linear in my I, and my AI square will write all present in the C. And if I want to put this constraint, and what happened is under that invariant condition, my double matrix even have not computed this matrix M is already completely parameterized by this n-1 variable. So that is in a way is if you without that to look at the double, and will be a lot of things free and very difficult to control. But if you're on the invariant requirement, and even now you already completely parameterize this into n-1 variables. So now I'm ready to put my double equation and to determine what are the C related to my phi's. And it's very nice. And if I only look at the residue at lambda equal infinity, and I already got determined all these C's. And the constant term will give me the double transformation, but of course now written into C variable, I have to go back to my phi variables. So if you look at, if I compute the derivative, because it's exponential, that is very good. And then all things, I can write in terms of s minus 1 phi x, phi k. And the matrix involved is a very neat matrix. That one is non-degenerate determinant is not equal 0. So which means from that and this C, I can get system for my phi x, that is my double transformation. But now the double transformation is not evolutionary, because evolutionary you want to write as phi x k equals something. But now it's s minus 1. You have to invert it. So I need to hurry up. So I work out for n equals 3 explicitly, and to fit my formula in to this slide, what I did is I did a simple transformation, and for the phi, and introduce new variable u and v, and write it nicely here, and just explicitly show you that is not evolutionary. So now I want to make it evolutionary. I already have double. I will going to backwards look at what u will make evolutionary. So and what I'm doing is I simply just say, okay, I move my m to here, and then m inverse is have, if you m have pole at mu, and the inverse I will have pole at 1 over mu. And then the old u have pole at 0 and infinity. It's somehow not fit. And I want to be consistent with my double transformation. So in a way, I make my new u with the same pole as my m. So that is the trick we put in. And it's worked. Because if we do the make this ansatz, and I will also take this generic orbit at mu, and now we got my, now say x is right into this form. So of course here, this its notation is in the product of two vectors, and this minus 1 is shift inverse. And from what we know, and how C related with phi, and the matrix I write out, that is non-degenerate, you can invert it, and that you can get that is evolutionary. That is a theorem. So I don't think I have time to sketch. Oh, that I want to mention. So if you look here, I have C, I have B, and I have A. And B is linear in A, and A is related to C, but the expression right as A square. So I don't like that, because which means if I want to substitute in, I will have nasty square root. So what you can do is, instead of you put a constraint, you could compute the evolution on your A, and which by adding double the dimension of your component, you got a nice evolutionary system. So I'm not to go for scratch the proof. And of course, now you're ready, you have your double, and now in this direction, you have your linear map S, and then that is a constraint on everything, and you have another one, and you by Bianchi commutation, and you can write out the discrete equation. So here I will not show you the discrete equation because we have not managed to put in the neat form. That is, as I said, that is work in progress. So let's say what going on. So that is the first example, which your double transformation is on the reduction group involve both inner and outer automorphism. Because we not even, if you go back, we also did minus Q, this A transpose, that is outer automorphism for your Lie algebra. And the idea to make it evolutionary flow for your double matrix, that is purely based on observation, and we have worked out that is worked for all ABS lists. We can do it. And this, of course, that is the first example. The the derived discrete system will be new, and that we will look at the other integrability properties. Okay, I think it's good time to stop here.
Okay, then let's take the speaker again.